All right, we're now going to take a look at pages 3 and 4 of our Unit 5 notes, the periodic law. And we're going to talk now about some of these, the different blocks of elements in the periodic table as related to electron configuration. Okay, so I'll just scroll up just for a real briefly. Just going to scroll up. Whoops, there we go. Okay, remember based on electron configurations of the elements, the periodic table can be divided into 4 blocks. We have the S, P, D, and F blocks. Okay, so we're going to look at the S block elements, which are groups 1 and 2, elements that are in groups 1 and 2. So, the outermost energy level of the S block elements ends with XS1 or XS2, with X being the principal energy level that the element occurs in on the periodic table. So with X, there it is, with X being equal to the period number, which is the highest occupied energy level, in other words. So every S block element ends in either S1 or S2, and before that S, this is in the electron configuration, you're going to have a number, and the number will be equal to the period number, which does represent the highest occupied energy level. Now there are 2 groups in the S block. There are groups 1 and groups 2. Group 1, we have already learned this before, but we're going to just review vocab here, and this is part of the vocab for this unit. We have the alkali metals. The alkali metals are elements that are in group 1 of the periodic table. So the elements that are in that first column on the periodic table, and the alkali metals include lithium, sodium, potassium, rubidium, cesium, and francium. Those are elements that are in group 1 of the periodic table. Those are the alkali metals. Now, hydrogen is arranged in this group, in this column, but is actually in a separate group all of its own. Hydrogen does not belong to the group 1 elements. Hydrogen is in a group all by itself. But it is arranged in this group because it does end in S1. It's 1s1 is its electron configuration. Now, all of the alkali metals electron configurations end in XS1, as it says up here, X being the period number. X is equal to period number. The alkali metals, as we may have already learned, are the most reactive of all metals, and they are not found in nature as pure elements. They are so reactive that you just don't find them in their pure form in nature, because if they're in a pure form in nature, they will immediately react with something and form a chemical compound. So elements in group 2 are the other elements in the S block. Elements in group 2 of the periodic table are the alkaline earth metals, and those consist of beryllium, magnesium, calcium, strontium, barium, and radium. Those are the alkaline earth metals. All of the alkaline earth metals end in XS2, and this is why these elements are called the S block elements, because their electron configurations end in S, either S1 if they're the alkali metals, or S2. And again, X is equal to the period number that the element occurs in within the periodic table, and it also represents the highest occupied energy level. Okay, the alkaline earth metals are the second most reactive of all metals, and these are not found in nature as pure elements either. Because they are so reactive. So beryllium, magnesium, calcium, strontium, barium, and radium are very reactive metals as well, very reactive elements, just like the alkali metals, just not quite as reactive. But they're both in the S block because their electron configurations end with S1 if they're the alkali metals, or S2 if they're the alkaline earth metals. All right, now we're going to talk about hydrogen and helium real quick, little detour with hydrogen and helium because they are exceptions to these electron configurations being placed in particular blocks. So hydrogen and helium are special cases in the classification of elements. So we're talking about them right now. Hydrogen first. Hydrogen's electron configuration is 1s1. It has 1 electron, and we know that the very first orbital that is filled is the 1s orbital, and if there's only 1 electron, it's just 1s1, and there's your electron configuration for hydrogen. It is 1s1, but it does not share the same properties as elements in group 1. Hydrogen is a unique element. Hydrogen is a unique element. And it's unique for a few reasons. The first, just a couple of little factoids here. Hydrogen, number 1, it is the most common element in the universe. In fact, there's 9 times more hydrogen than all other elements combined. So it is the most common element it is the most common element in the universe by far, 9 times more than all other elements combined. And that's because the most common object in the universe is probably a star, and stars are primarily made up of hydrogen gas. Secondly, the properties do not closely resemble those of any other group. It is unique in the sense that it's the most common, by far the most common element. It is the simplest of all elements, just has 1 proton and 1 electron, at least most hydrogen atoms, that's all they consist of. And it's just unique, and its properties are just different. It's not a metal, so it can't be placed in that group 1, alkali metals. Even though it ends in S1, it's not a metal in its properties. It is just unique. So that's just something you just have to know. The second exception we'll look at is helium. Helium is a little less exceptional. The one thing that you'll notice about helium is that its electron configuration is 1s2, but it doesn't belong in group 2, which all the other elements that end in S2 are in group 2. This is the only one that's not. It belongs to group 18, not group 2. And this is because helium is in the first period, and the first, it just has 1 principal energy level, and we know if there's only 1 principal energy level, that means there's only 1 orbital shape, and it is the s orbital shape. This is stuff we learned in the last unit. And that s orbital shape is a sphere, and there's only 1 of them, and it can only hold 2 electrons. When it holds 2 electrons, which is all that helium has, it is filled. And this is why it's actually in group 18, because its highest occupied principal energy level is full. That makes it chemically stable. And because it is chemically stable, it is like the noble gases, and as a result, helium is unreactive. It doesn't want to react, so that's why it's placed in group 18 with all the other noble gases, which have full highest energy levels, and as a result, they're all unreactive. And that's why helium is an exception. It's placed in that group 18. Okay, so those are some exceptions. So we talked about the S block. And then why hydrogen and helium don't belong in the S block. But the S blocks are very predictable. Group 1 elements, the alkali metals, all end in S1, and their electron configurations. And that means they have 1 valence electron as well. Maybe I should note that here. I don't think I have that in the notes. I think I need to put that in the notes. I think you should add this here somewhere. 1 valence electron. That's very significant, actually, for chemical behavior. It might show up later in the notes. And alkaline earth metals have 2 valence electrons. And this is why they have similar chemical behavior. This is why they have similar chemical properties, chemical behavior, because they have similar numbers of valence electrons. Okay, now let's take a look at the next block of elements based on electron configuration. Those are the p block elements. So the electron configuration of the p block elements, those are elements that are in groups 13 through 18. The electron configuration of the p block elements will end with xp1 to xp6, again with x being equal to the highest occupied energy level, which in the case of the p block elements is the period number, just like in the S block. So all the p block elements, all the elements that are in groups 13 through 18, will end in some variation of p1 up through p6, and the x before the p, which is the last place you put electrons, will be a number that is equal to the period number, because that's the highest occupied energy level. So p block elements contain some metals, all nonmetals, and all metalloids, except hydrogen, of course, because hydrogen is in a group all of its own. But all the nonmetals are in the p block, all the metalloids there, and even some of the metals are in the p block. Kind of wish I had a periodic table here in front of you. And there we have a periodic table. Ask and you shall receive. Okay, so just want to point out again, the S block elements are those elements that are in groups 1 and 2, although hydrogen is in a group all of its own, so it's not in the S block. So it's lithium down through francium in groups 1, beryllium down through radium in groups 2, and these all end in, this ends in, 2s1, this is 2s2, let me start over, sorry about that. This would be 3s1, this is 4s1, 5s1, and then so on and so forth. In beryllium, this would be 2s2, 3s2, 4s2, and then 5s2, and so on. And then the p block elements are those that are in groups 13 through 18. So over here we have 13 through 18 from boron down. and from helium down. Now helium is an exception also because helium ends, the electron configuration of helium is 1s2. So basically helium is also an exception in it's not in its own group though, it is put into the noble gases, but it's the one noble gas that doesn't end in P. All of these other ones end in X. So if they're in groups 13, they're going to it's going to be XP1. If they're in groups 14, it's going to be XP2. Or excuse me, groups 14, XP2. If they're in groups 15, it's going to be XP3. These will be XP4. X is equal to the period number. This will be XP5. And over here we have all the noble gases, XP6, again with the exception of helium, which ends in 1s2. So there's your S block over to the left side. In your P blocks here, all your nonmetals are here except hydrogen in the P block. All of your metalloids are in the P block as well, except and even some metals like aluminum, thallium, lead, and tin, and etc. Okay, so let's go back to the notes. All right, and now we're going to continue on with page 4 of the notes. Okay, so now this figure below, the figure below here, shows the distribution of metals, nonmetals, and metalloids on the periodic table. So now we're going to shift and start talking a little bit about other things other than these the S block and the P block and the F block and the D block, although those may come up again as we go. But here's a periodic table that's drawn here where we don't have the symbols of the elements here, but what we do have here is a little key that tells you that all the clear squares are metals, or all the white squares, all the light gray squares are the nonmetals, and all the darker gray squares are the metalloids. Okay, so it's going to go through more vocabulary here. So halogens are elements in group 17 of the periodic table, and the 17 may have already been filled in for you, but the halogens are group 17. So if we're looking at this schematic drawing, they're all going to be right here. So these are some different groups that you have to now know in the periodic table. So we have fluorine, chlorine, bromine, iodine, and astatine. If you go down group 17, all of the group 17 elements end or in the same electron configuration, and see if you can figure it out. These are all P blocks. Okay. All of the noble gases in the P6, that's maybe a little bit of a preview, all of group 14 elements in the P1, and then we have all of group 15 will be P2, 16 will be, 14 is P2, 15 is P3, 16 is P4, and then all of the group 17s are going to end in P5. Okay, so all end in XP5 with X again being equal to the period number. The halogens are the most reactive of all the nonmetals, and halogens also have a special property or characteristic, and we talked about this when we did the flame test. I talked about what a salt is, but halogens react with most metals to form salts. So the definition of a salt is a group 17 element that is bonded in an ionic bond to a metal. That's what a salt is, and so it's a halogen bound to some metal, like sodium is an alkali metal in group 1, bonded to chlorine, which is a halogen. So a metal with a halogen gives you a salt. So the high reactivity is due to the presence of 7 electrons in their highest occupied energy level. And this is 1 electron short of being full and stable like the noble gases. So now the halogens, you should understand, the halogens all have 7 valence electrons. 7 valence electrons. So those are electrons in the highest energy level. If we take a sample halogen like chlorine, for example, chlorine, its electron configuration is 1s2, 2s2, 2p5. Actually, sorry, I misstated. I'm doing fluorine. So this is fluorine, not chlorine. Chlorine is too long for this example. But fluorine is 1s2, 2s2, 2p5. And when we're looking at valence electrons, we're looking at electrons in the highest principal energy level. So when we look at fluorine, level 2 is the highest level. We see we have 2s2 and 2p5. The 2s has 2 electrons in it, and the p has 5. So 2 plus 5, that is 7 electrons. 7 electrons in level 2. In level 2. So that's 7 valence electrons in the highest level, because level 2 is the highest level for fluorine. I didn't want to do chlorine because it would be too long. The configuration is too long for this example. But anyway, that 7 valence electrons is really important because it means that this element is very, very close to having a full highest energy level, and that is the goal in life of every element, is to have a full highest energy level. The closer elements are to having a full highest energy level, the more reactive they are. And so halogens are very reactive because they're so close. They just need 1 electron to fill that highest energy level. So they are very, very reactive because they want to get that full highest energy level. And we'll talk more about that reactivity as we move on later. Okay, let's just finish up here. So then we'll take a look at the noble gases. Mendeleev's periodic table was notable when Mendeleev did his table because it completely skipped the elements in group 18. And this is because none of these elements had been officially recognized in 1869. In fact, most of them had not even been noticed at all. And this is because of the fact that they are unreactive and because they are invisible gases. They're invisible gases, all of them, neon, helium, etc. They're all invisible gases and are almost completely unreactive. So that makes them really hard to detect. Now, between 1894 and 1898, a Scottish chemist named Sir William Ramsay discovered the first 5 noble gases, that is helium through xenon, and placed them in this new group, group 18. So noble gases, by definition, are elements in group 18 of the periodic table. And we have helium going down, helium, neon, argon, krypton, xenon, and radon. All of these end in xp6, as I've already noted, except helium, as I've also already noted, which ends in 1s2. Now because, and I've talked about this already earlier in the video, because their highest outer energy level has 8 electrons, they rarely react with other elements or form compounds at all. So they are essentially unreactive, except most of them are almost completely unreactive, except for the larger ones, which can in some cases form chemical compounds. And that's really because they're so large. Electrons are easily sort of taken away because the attraction is very weak when you have really large atoms. The attraction towards those electrons in the highest levels. We can get into more of that later, but just understand that these noble gases are basically essentially unreactive. And we go up to the first, the second noble gas, neon, it's 1 above fluorine. So if we look at that electron configuration for neon, we see that it's 1s2, 2s2, 2p6. So again, the highest energy level is level 2, and there's electrons in 2s and 2p, and there's 2 electrons in the S shape of level 2, and there's 6 electrons in the p shape, and therefore they're both filled. Those highest energy levels are completely full. That means you have 8 valence electrons, 8 valence electrons, or 8 electrons in the highest energy level, and so they're full, and that's why they're super stable and are essentially unreactive. Okay, now the D block elements are elements that are in groups 3 through 12. With electron configurations, the D block elements, and this is a little complicated if you just look at it, but basically x minus 1 D1 to x minus 1 D10. Basically, again, x is equal to the highest occupied energy level or the period number. So if you're looking at period 4, then all the D's, elements that are in period 4, they end in period 4 minus 1. So that's 4 minus 1, that's 3. They end in 3D1 to 3D10. And this agrees with electron configurations we've been doing for these from the previous unit. These are called the transition elements or the transition metals. These are the D block elements in groups 3 through 12. And they are metals with typical metallic properties. These are actually some of the most common or most well-known metals. Transition elements generally have a high luster and are good conductors. They're very metallic in terms of what we think about with metals. They're shiny, they're very good conductors of heat and electricity, and they're also not very reactive. And so they may occur in nature as pure elements. So we do see things like palladium, platinum, gold, silver, copper. These are elements that they're reactive, but not super reactive. So we do actually see them in nature as pure elements, more common or more easily recognizable as metals. These are some, like I said, of some of the most well-known metals. Things like gold, silver, copper, mercury, platinum, titanium, and nickel are all examples of these transition elements that are in the D blocks. And they all end in the principal energy level -1 and D to D1 up to D10. Okay, all right, that's it for pages 3 and 4.